2 decades ago, the United States was a clear global leader in science, technology, and innovation. Today, by many internationally recognized measures, China has overtaken U.S. leadership in 57 of 64 critical technology fields, including base and production technologies, and has surpassed the United States in total R&D investment. China should no longer be viewed only through the lens of intellectual property theft. It has become a major technological force with modern infrastructure and a capable science, engineering, and manufacturing workforce. China now leads the world in highly cited top-tier research publications and international priority patent families across critical technologies, including biotechnology, quantum information science and technology, robotics, semiconductors, and artificial intelligence. It has strengthened its own IP system and the protections to counter areas where the United States leads, while substantially increasing its influence in international standards. Meanwhile, the United States has allowed the strength and enforceability of our intellectual property protections to decline, weakening the global value of American inventions. Measuring strategic advantage requires more than counting publications, patents, workforce, or dollars spent. It requires an ecosystem view, considering the fundamentals and enablers of strategic competitiveness, research and innovation capacity, manufacturing capability, capital, workforce, standards leadership, trusted supply chains, and enforceable IP rights. The CSIS Tech Edge analysis integrates these factors, showing U.S. leadership advantages continue in stack and precision technologies. Achieving the technological dexterity to build ecosystem strengths across multiple technology domains is a strategic national imperative. Public R&D is indeed our great engine of productivity, startup formation, and national competitiveness. But recent disruptions and self-inflicted wounds have slowed our research enterprise and weakened American capacity, while our competition is increasingly strong in running this accelerating race. To translate invention into impact, preserving the integrity of the Bayh Dole Act is essential. We must modern Stevenson-Weidler, learning from the NIST Green Paper to unleash American innovation, and to finally implement the return on investment legislative proposal for effectiveness, speed, and productivity in R&D collaborations. Our security depends on the reliability and effectiveness of our R&D, intellectual property, standards, manufacturing, and innovation ecosystems. We have much work to do in education, preparing leaders at all levels for building domestic workforce, and also continuing to attract and retain talent globally to strengthen our innovation economy. We must enforce the rights of American innovators both here and around the world, incentivize participation in standards development, and invest strategically to enable new manufacturing, innovation, and production capabilities. International scientific collaboration with both trusted partners and our competitors is a vital strategic asset. It accelerates discovery, expands our talent pool, secures critical supply chains, and projects American leadership. To defend our interests, engagement in global standards and metrology to support trade must be open, fair, and strategically sustained. Navigating intense competition, we must also recognize the profound strategic threat of allowing the rest of the world to dictate global technical standards. Finally, we must make the U.S. innovation system ever more agile, faster, reducing administrative burdens, modernizing law and practice, and removing barriers to encourage investment. We must defend our innovators at home and abroad against mercantile and malign threats. Thank you for this committee's important work to secure U.S. science, technology, and innovation leadership for our economic and national security. I look forward to your questions.
Thank you, Dr. Copan. Dr. Indy, you're recognized for 5 minutes.
Thank you, Chairman Budd, Ranking Member Baldwin, members of the subcommittee. Thank you for the opportunity to testify. I teach and research bioengineering at Stanford. I also direct the Biostrategy and Leadership Initiative at the Hoover Institution. I've co-founded companies that build DNA. My wife has left academia to start a company that brews the ingredients going into Narcan and other essential medicines. I want to acknowledge the work of the National Security Commission on Emerging Biotechnology, chaired by Senator Young. The Commission's work is the best work I've seen in this town on biotechnology. I want to emphasize the Commission's most recent finding, the recommendations from the Commission, have been read by Beijing and are being implemented by Beijing. Which brings us to this hearing. Chairman Budd, thank you again for your framing of the topic. Most topics on competition ask questions like, who's in the lead? But you're asking a more important question, how would we know? And so that brings us to measuring what matters. Let me tell you a story about being in Paris last fall for the Genetic Engineering Olympics I started at MIT over 20 years ago. 5,000 20-year-olds from all over the world, most now from China, and I found a young gentleman, a 20-year-old from Shanghai, dressed up like a crawfish, this big red costume. I said, what are you doing? He says, well, I'm working on engineering enzymes, bioengineering enzymes to degrade the material in crawfish shells so you could repurpose those materials to make new things like clothing and shielding and stuff like that. I'm like, well, why? He says, because someday there's going to be Chinese astronauts on Mars. And when they're on Mars, they're going to need to have a spicy crawfish soup for lunch. And I want to make sure there's a closed-loop crawfish bioeconomy and material manufacturing economy on Mars, because it's going to be really important that they have that spicy crawfish soup for lunch so that they remember that they're Chinese on the red planet. That's what we're competing with. The vibe. The vibe is good in Beijing. How do we measure that? Biology is not like other technologies. Imagine if you could somehow feed your cell phone sand, and it would get bigger and bigger and bigger and divide, and then you'd have 2 cell phones. Like, that's what biology does on the regular. That means we don't really know how to measure biology like we know how to measure other forms of emerging technology. Let me give you an example, more specific. Who's the best in the world at building DNA? DNA is the molecule that encodes all of life, and it's probably the industrial polymer of the 21st century. Who is the best in the world at building DNA? Nobody in the United States government knows. Not NIST, not the National Science Foundation, not the Department of Energy, nobody I know in intelligence. We could answer these questions if we did something about it. If you think about the basic sciences in high school, there's physics, and there's chemistry, and there's biology. Those are the big ones. And if we think about NIST, NIST has the physical measurement laboratory for physics, where you get the kilogram and the meter and the second right. And NIST has the material measurement laboratory for chemistry and a little bit of biology. But it doesn't have a biomeasurement laboratory yet. Gosh, we could really use one. There's many things the Congress could do, but getting a biomeasurement laboratory at NIST is, I think, one of the high leverage things that would let us measure what matters and get ourselves in a good position for competing. Don't take my word for it on that one. Your US-China Commission last year made getting a biomeasurement laboratory at NIST their #4 most urgent recommendation, so it's not just me. Thanks very much for the opportunity to testify today. I look forward to your questions.
Thank you, Dr. Indy. Dr. Atkinson, you are recognized, and thank you for wearing some Carolina blue on your necktie.